Earth feels permanent. The sky returns each morning, the oceans hold their shape, and the ground beneath everything seems still. But far beyond human time, none of it stays the same. The sun grows brighter, the air begins to change, the oceans slowly retreat, life itself fades, layer by layer, until Earth becomes something almost unrecognizable. This is not science fiction. It is the long, strange future written into the laws of the cosmos. If this kind of deep time journey is interesting, please like the video, subscribe to the channel and share it with someone who loves science. Earth moves around the sun in a path that remains familiar for very long spans of time, while the source of its light changes slowly. The sun is not a fixed lamp, it is a star that grows brighter as it ages. In its core, hydrogen nuclei join together to form helium, and this fusion releases energy. Over immense stretches of time, the balance inside the sun shifts. Helium builds up in the center, the core becomes denser, and the rate of fusion gradually rises. Because of this slow internal change, the sun sends more energy outward than it did in the distant past. The increase is steady, not sudden. It is measured not in days or centuries, but in hundreds of millions and billions of years. From far above Earth, the first sign of this future is simple. More sunlight reaches the planet. Earth does not move closer in any large or lasting way during this stage. The main difference comes from the sun itself. The stream of light and heat arriving from space becomes slightly stronger over time. At first the change seems small. A small rise in solar output spread across a whole planet may appear gentle. Yet Earth is a system that responds to small shifts when those shifts continue long enough. The upper boundary of the atmosphere receives the change first, because that is where sunlight arrives before it passes through air, cloud, or dust. At the edge of space around Earth, sunlight carries energy in several forms. Some arrives as visible light, the part that human eyes can detect. Some arrives as infrared radiation, which is often linked with warmth. Some arrives as ultraviolet radiation, which has enough energy to break apart certain molecules. The atmosphere does not treat all of this incoming energy in the same way. Different gases absorb different wavelengths. Oxygen and ozone are especially important high above the surface because they interact strongly with ultraviolet light. Nitrogen, the most abundant gas in the atmosphere, plays a quieter role in absorbing incoming sunlight directly, though it shapes the structure and motion of the air around it. As the sun brightens, the total amount of energy increases, and the atmosphere receives more of each part of the spectrum. Observations of stars like the sun and models of stellar evolution show this trend clearly. The exact pace over very distant future intervals depends on well-understood stellar physics. The broad direction is not in doubt. More energy arrives at the top of Earth's atmosphere, and Earth must respond by reflecting some of it back to space and by sending thermal radiation outward. A planet stays in energy balance when incoming energy and outgoing energy are equal on average over time. When incoming energy rises, the rest of the system adjusts until a new balance is found. This balance begins with reflection. Earth does not absorb all sunlight. A portion is sent back to space by clouds, airborne particles, ice, bright land surfaces, and the atmosphere itself. This reflectivity is known as albedo, meaning the fraction of incoming light that a surface or planet reflects. A bright object has a high albedo. A dark ocean has a lower one. From the outer view, Earth is neither highly bright nor highly dark. It reflects a modest share and absorbs the rest. In the slow future described here, the first scientific task is to understand how the planet handles the extra incoming sunlight before attention turns to deeper changes below. Some of the added energy is absorbed high in the atmosphere. Ultraviolet radiation is especially important in the upper layers because it splits oxygen molecules and helps create ozone. Ozone then absorbs more ultraviolet light. This process warms the stratosphere, the layer above the turbulent lower atmosphere. It also protects lower regions from much of the most energetic solar ultraviolet radiation. In Earth's future, a brighter sun strengthens this pattern by delivering a greater ultraviolet flux. The chemistry remains governed by known reactions among oxygen, ozone, nitrogen compounds, hydrogen compounds, and sunlight. The detailed future abundance of ozone depends on several interacting factors, and some aspects remain uncertain over the longest timescales. But the basic principle is clear. More solar energy means more heating and more photochemistry in the upper air. The upper atmosphere also expands when it becomes warmer. Hotter gas occupies more volume. In the thermosphere, where the air is extremely thin and temperatures respond strongly to energetic radiation. This expansion can be pronounced. Even now, changes in solar activity cause the upper atmosphere to swell and contract. Over much longer intervals, a brighter average sun shifts the background state in the same direction. The atmosphere at great height becomes more extended. This does not mean the air becomes dense there. It remains very thin, but its structure changes. Molecules and atoms at the top of the atmosphere gain more energy, and some escape to space more readily than before, especially the lightest gases. Hydrogen is the easiest gas for Earth to lose. Near the top of the atmosphere, hydrogen atoms can move fast enough to escape Earth's gravity. Much of this hydrogen comes from water molecules that are broken apart by sunlight. In the present atmosphere, most water remains far below these upper levels, limited by the cold structure of the middle atmosphere. In the far future, the long rise in solar energy affects this arrangement by altering temperature and transport through the atmosphere. Even before major surface consequences appear, the outer atmosphere becomes a more active place for chemical splitting, heating, and loss of the lightest particles to space. This is one of the earliest planetary responses to a brighter star. Earth also radiates energy outward. After sunlight is absorbed by the surface and atmosphere, the planet emits thermal infrared radiation back to space. This outward flow is the planet's cooling mechanism. From the outside, the future Earth is a world trying to keep pace with a slowly intensifying sun. The top of the atmosphere is where that accounting is completed. Incoming solar energy arrives there. Reflected light leaves there. Outgoing thermal radiation leaves there as well. The long story of Earth's future begins with this accounting becoming harder to maintain in the old way. Nothing dramatic appears in a single human lifetime. The change remains almost invisible on ordinary scales. Continents, oceans, and clouds still lie beneath, and the planet still turns with the same steady rhythm. Yet from the distant scientific view, the first region to register Earth's strange future is the outer envelope of air touched directly by sunlight. It warms, expands, and processes a stronger flow of radiation. The balance at the top of the atmosphere slowly shifts. The planet still remains recognizably Earth, but the conditions that support that recognition begin to move. Above the surface, but below the near vacuum of space, Earth's atmosphere forms a layered envelope shaped by sunlight, gravity, chemistry, and motion. As the sun slowly grows brighter, this envelope changes in ways that are at first subtle and then increasingly important. The added solar energy does not simply warm all air equally. Each layer responds according to its composition, its density, and the kinds of radiation it absorbs. In this long future, The upper and middle atmosphere become a place of shifting temperature structure, changing circulation, and gradually altered behavior of water vapor. The atmosphere is arranged in layers because temperature does not change with height in a single smooth way. In the troposphere, the lowest layer, temperature usually falls with altitude. Above it lies the stratosphere, where temperature rises with height because ozone absorbs ultraviolet light. Higher still are thinner layers where energetic solar radiation becomes even more important. In the present section, attention remains on the upper and middle atmosphere rather than on the surface below. These regions act as a gate through which energy passes and as a filter that determines how gases are heated, mixed, and transformed. A brighter sun increases the amount of radiation entering this system. In the stratosphere, ozone remains central. Ozone is a form of oxygen made of 3 oxygen atoms rather than 2. It forms when ultraviolet light breaks ordinary oxygen molecules apart, allowing single oxygen atoms to join with intact oxygen molecules. This ozone then absorbs more ultraviolet radiation and warms the surrounding air, with stronger solar input over very long time scales. The pattern of ozone formation and destruction continues, but under changed conditions. More ultraviolet light tends to support stronger photochemical activity, while temperature changes and shifting concentrations of reactive gases alter the details. Observations and models indicate that the broad structure of a sunlit, ozone-heated stratosphere remains, though its exact future composition is not perfectly certain over the longest intervals. This warming aloft affects the vertical profile of the whole atmosphere. The temperature structure of air matters because it controls stability. Stable air resists vertical mixing. Unstable air allows rising and sinking motion more easily. In the stratosphere, warming from ozone tends to keep that layer comparatively stable. As solar energy rises, the middle atmosphere may become warmer in some regions and at some heights, while other changes in chemistry alter how heat is distributed. The result is not a single uniform increase, but a reorganization of layers. Air at one height absorbs radiation, expands, and shifts pressure surfaces upward. This slow restructuring changes how waves and large-scale motions travel through the atmosphere. Circulation in the middle atmosphere is driven by differences in heating between equator and pole, by the rotation of Earth, and by upward moving waves from the lower atmosphere. Air does not stay still. It rises in some places, drifts across long distances, and sinks elsewhere. In the stratosphere, this broad movement helps transport ozone, water vapor, and trace gases around the planet. In a brighter future, temperature contrasts may change, and so may the speed and pattern of this circulation. Some features can be estimated from physical principles, while others depend on complex feedbacks that remain difficult to resolve over such long spans. It is known that changing radiation changes pressure gradients, and pressure gradients help drive motion. It is also known that the middle atmosphere responds to even modest changes in forcing when those changes persist long enough. Water vapor becomes especially important in this region because it is both a greenhouse gas and a source of hydrogen loss at high altitude. In the modern atmosphere, most water vapor stays in the lower air. The reason is largely thermal. As moist air rises, it cools. Cooling causes water vapor to condense into droplets or ice, which then fall back downward. This process leaves the upper atmosphere comparatively dry. A particularly cold region near the boundary between the troposphere and stratosphere acts as a bottleneck, limiting how much water reaches higher levels. This boundary is often called the cold trap because it traps water below by freezing or condensing it out before it can rise farther. As solar input slowly increases, the temperatures and circulation around this bottleneck begin to change. A warmer lower atmosphere can carry more water vapor because warm air holds more water before condensation begins. Even without describing the surface in detail, the atmospheric consequence is clear. More moisture enters the lower part of the air column, and the efficiency of the cold trap becomes increasingly important. If the cold trap weakens, more water vapor passes into the stratosphere. Once there, water is exposed to stronger ultraviolet radiation and can be broken apart. The hydrogen released from this process is light enough to escape more easily from the top of the atmosphere. This does not happen all at once. The atmosphere first moves through a long interval in which the upper and middle layers are simply a little more humid than before, or more variable in humidity, depending on circulation and temperature. Small shifts matter because stratospheric water vapor affects both radiation and chemistry. It absorbs infrared radiation and influences how heat is retained and released. It also participates in reactions involving ozone and hydrogen-bearing compounds. In this way, water vapor is not only transported by the atmosphere, it also changes the atmosphere that transports it. Clouds in the highest parts of the atmosphere may also shift in abundance and behavior under changed temperatures. Thin icy clouds near the top of the lower atmosphere influence radiation by reflecting some incoming sunlight and trapping some outgoing heat. Their future response depends on moisture supply, vertical motion, and temperature. The precise balance remains uncertain in detail, but the general scientific picture is that a brighter sun pushes the atmospheric system toward a state with more water moving upward and more radiative complexity in the middle levels of the sky. The atmosphere also responds through pressure and height. As it warms, the thickness of layers increases. A warmer column of air occupies more vertical space between one pressure level and another. This means that characteristic pressure surfaces rise higher. The entire envelope appears slightly puffed upward. Satellites in low orbit already experience changes in drag when the upper atmosphere expands during periods of increased solar activity. Over very long future timescales, a brighter average sun sustains a more expanded upper atmosphere as part of the background state. This is another sign that the air envelope is not fixed. It breathes slowly with energy. Throughout this period, the atmosphere remains recognizably layered and dynamic. Nitrogen and oxygen still dominate its bulk. Ozone still filters ultraviolet light. Air still moves in broad planetary patterns shaped by rotation and sunlight. Yet the balance within these patterns drifts. The middle atmosphere becomes warmer in important regions. Water vapor begins to reach higher levels more readily, and photochemistry becomes more active under stronger radiation. The sky above Earth is not a passive shell. It is an evolving system, adjusting layer by layer to a star that steadily brightens. Earth's long climate stability depends on a slow exchange between air, water, and rock. This exchange does not keep conditions fixed in every era, but over very long spans it helps prevent the planet from moving too far toward extreme heat or extreme cold. In the future, as the sun continues to brighten, this protective balance weakens. The change begins not with a sudden break, but with a gradual loss of the processes that once kept surface conditions within a narrower range. The atmosphere remains present, the planet still reflects and emits energy, and winds still move across the globe, yet the old climate regulation becomes less effective. A central part of this regulation is the carbon cycle. Carbon moves between the atmosphere, the oceans, living things, soils, and rocks. Over geological time, one of the most important pathways involves carbon dioxide in the air, reacting with water and minerals at the surface. Rainwater absorbs carbon dioxide and becomes weakly acidic. When this water meets exposed rock, especially silicate rock, it slowly breaks minerals apart. Silicate rock is rock built mainly from silicon and oxygen joined with metals such as magnesium, calcium, sodium, or potassium. This weathering process removes carbon dioxide from the atmosphere and eventually stores carbon in sediments and crustal materials. Volcanoes and other geological processes return some of that carbon dioxide to the air over immense time. This exchange acts as a thermostat. When climate warms, weathering often speeds up, drawing down more carbon dioxide and tending to limit further warming. In Earth's future, the problem is not that this system disappears at once. The problem is that the conditions needed for it to regulate climate in its familiar way begin to erode. A brighter sun drives stronger warmth across the surface. Higher temperatures increase evaporation and intensify the movement of water through the air and across rock, at least while abundant water remains available. This can increase weathering for a time, and the increased weathering removes more carbon dioxide from the atmosphere. On shorter geological scales, this seems protective. It pulls greenhouse warming downward. Yet the sun's continued brightening does not stop, and the thermostat has a limit. The atmosphere can lose only so much carbon dioxide before another boundary appears. Carbon dioxide is a greenhouse gas, meaning it absorbs outgoing infrared radiation and helps keep heat near the surface. Earth needs some carbon dioxide for warmth, but the carbon cycle also links carbon dioxide to life and rock chemistry. As weathering continues under increasing solar energy, the concentration of carbon dioxide in the air gradually falls. This decline may unfold over hundreds of millions of years. Models and geochemical reasoning indicate that the amount can eventually become very low by modern standards. At that stage, the atmosphere still contains nitrogen, oxygen changes through time, and water vapor remains important, but the familiar balance of gases that supports the present biosphere no longer holds. The weakening of climate stability appears here as a narrowing of options. In earlier times, if the planet warms somewhat, increased weathering can pull carbon dioxide down and reduce greenhouse trapping. In colder conditions, weathering slows, volcanic sources continue, and carbon dioxide can build up again. This push and pull provides flexibility. Under a brighter sun, however, the drawdown of carbon dioxide can proceed so far that there is little room left for adjustment. The climate system can no longer compensate by taking away much more greenhouse gas, because too little remains. Even if weathering continues, its ability to stabilize temperature weakens because the solar forcing has grown too strong relative to what the carbon cycle can offset. The surface climate at this stage remains governed by energy balance, but the details are increasingly shaped by water vapor. Water vapor is also a greenhouse gas, and it responds directly to temperature. Warmer air can hold more moisture. This creates a feedback, which is a process that amplifies or reduces an initial change. In this case, the feedback is positive. More solar heating raises temperature, warmer air holds more water vapor, and more water vapor traps more heat. This does not mean the planet immediately becomes unrecognizable. It means the climate becomes more sensitive. The old rock-based thermostat is still present, but it works more slowly and with less leverage than before, while water vapor responds quickly and strongly within the atmosphere. Clouds remain part of the balance as well. They reflect sunlight and also trap heat, and their net effect depends on height, thickness, and distribution. A warmer world may produce cloud changes that alter planetary reflectivity, but the direction and magnitude of those changes are complex. Observations of modern climate and numerical models show that cloud feedbacks can matter greatly, though the exact long-term response of clouds in a far future Earth remains uncertain. What is well supported is the larger pattern. As the sun brightens and carbon dioxide falls, the climate becomes more dependent on water vapor and less able to rely on long-term geological adjustment. The oceans still moderate temperature during this interval, because water stores and moves heat effectively. Large bodies of water absorb energy without changing temperature as quickly as land. Air and ocean circulation spread this energy across the planet. Even so, this buffering does not cancel the overall trend. The planet's average surface conditions continue to move upward. Seasonal cycles remain. Latitude still matters, and some regions stay less extreme than others. But the global background state drifts toward greater warmth. Ice and snow, where they persist, reflect sunlight. Yet under stronger solar input, these bright surfaces cover less area on average, reducing their cooling influence. Another part of the protective balance comes from the interaction between biology and the atmosphere. Living organisms affect carbon storage, soil formation, and gas exchange. In the current section, the focus remains on climate stability itself rather than on the detailed fate of ecosystems. But the link cannot be ignored. As carbon dioxide becomes scarce and heat rises, the living contribution to atmospheric regulation weakens. The biosphere no longer reinforces the old balance as effectively as before. The climate system increasingly depends on physical and chemical processes alone, and those processes are under growing strain. The result is not a world transformed in an instant, but a world drifting out of its long equilibrium. The atmosphere still circulates, rain still falls in many regions, rocks still weather, carbon still moves between reservoirs. Yet the familiar self-correcting behavior becomes less reliable. The sun adds energy faster, in the geological sense, than the slow carbon cycle can continue to compensate. Carbon dioxide falls toward levels that undermine both biological productivity and climatic flexibility. Water vapor grows more important as a source of greenhouse trapping. Earth remains a planet with air, oceans, land, and weather. But the balance that once made these parts work together in a more stable way begins to give way. Water covers most of Earth's surface for much of the planet's history, and this broad layer of liquid plays a central role in climate, weather, and chemistry. In the long future under a brighter sun, the stability of surface water begins to weaken. This change does not begin with all oceans vanishing at once. It begins with a slow shift in the balance between evaporation, condensation, rainfall, cloud formation, and escape to space. The surface still holds seas, lakes, rivers, ice, and groundwater for a very long time, but each part of that water system comes under growing pressure as solar energy continues to rise. Evaporation is the first clear sign. Liquid water at the surface absorbs heat, and some of its molecules gain enough energy to leave the liquid and enter the air as vapor. This process happens continuously over oceans and inland waters, and even from moist soils and plant surfaces. With a brighter sun, more energy reaches the ground and the sea surface. As temperatures rise, evaporation strengthens. Warm water loses molecules more readily than cool water, and warm air can hold more water vapor before condensation begins. This means that the lower atmosphere becomes increasingly humid over wide regions, especially above the oceans. At first, a more humid atmosphere does not mean a drier planet. It can mean more vigorous exchange. More water rises from the surface, more clouds form in some places, and more rain may fall where air ascends and cools. The hydrological cycle, meaning the continual movement of water through evaporation, clouds, rain, runoff, and return to the sea, becomes more intense while abundant liquid water is still present. Winds carry larger amounts of moisture. Storm systems can transport more latent heat, which is the energy stored when water changes phase without changing temperature. In this stage, Earth still behaves like a water-rich world, but the cycle becomes heavier with vapor and more demanding in energy. The difficulty lies in the long-term trend. As surface temperatures climb, the atmosphere carries more water not only near the ground but also through deeper layers. Some of this vapor rises high enough to approach the cold upper boundary that once kept most water confined below. If that boundary grows warmer or less effective, more water reaches the stratosphere. There, sunlight can split water molecules into hydrogen and oxygen. The oxygen may remain bound in atmospheric chemistry or react with surface materials over time. The hydrogen, being very light, can escape into space. This loss is small on short timescales but powerful over geological spans. Molecule by molecule, a portion of Earth's water inventory begins to leak away. Clouds continue to form, but their role becomes more complex. Low clouds often reflect incoming sunlight and help cool the surface, while high, thin clouds can be more effective at trapping outgoing heat. In a warming world with more water vapor, cloud patterns may shift in altitude, thickness, and location. Some regions may become cloudier, others less so. The precise global balance remains one of the difficult parts of climate science, especially for remote future states. Still, the main pattern is clear. A warmer Earth with more atmospheric moisture does not guarantee a stable water cycle. It can move toward a state in which evaporation and heat trapping grow faster than the cooling help provided by clouds. Rainfall also changes in distribution. Water does not fall evenly across the globe. It depends on circulation, temperature contrasts, ocean conditions, and topography. In a warmer climate, some places may still receive heavy rain for long intervals, while others dry more deeply. The familiar boundaries between wet and dry regions begin to shift. Subtropical dry belts can expand. Interior continents can lose reliable moisture. Lakes shrink if evaporation rises beyond the water supplied by rainfall and rivers. Rivers themselves depend on seasonal snow, groundwater recharge, and upstream precipitation, all of which are altered by long-term warming. The water cycle continues, but it becomes less generous to the land. The oceans remain the great reservoir. They slow the pace of change because they contain most of the planet's surface water, and because water requires large amounts of energy to heat and to evaporate. Yet even the oceans are not beyond this gradual loss. A warmer surface means stronger evaporation from the sea. Much of this water returns as rain, but not all of it remains safely within the lower system over immense spans of time. As more water vapor reaches high altitudes and more hydrogen escapes, the total amount of water on Earth begins to decline. This decline is slow compared with human history, but from a planetary view it marks the beginning of retreat. As oceans lose water, shorelines do not simply move inward in one smooth line. Local coastlines depend on basin shape, crustal motion, sediment, and remaining climate patterns. Shallow continental seas may retreat early in some regions. Inland basins may become saltier as evaporation removes pure water and leaves dissolved minerals behind. Salt flats can form where lakes once stood. Coastal wetlands may vanish or migrate. Yet during much of this long interval, the planet still contains vast seas. The change is measured not in the disappearance of water altogether, but in its declining security as a surface feature. Water also shapes temperature through its presence as vapor. As more water enters the air, greenhouse trapping strengthens. This further warms the surface and lower atmosphere, allowing still more evaporation. This is another positive feedback. It does not imply a runaway process at every stage, but it does show why the planet becomes increasingly sensitive once the air grows wetter. The oceans, once the foundation of climate stability, now also feed the mechanism that makes further warming easier. Beneath the surface, groundwater stores water in porous rock and sediment. Some deep aquifers may persist even as surface conditions become harsher. Springs may continue in isolated places where geology allows water to remain protected. Ice lingers longest where cold traps remain, especially at high elevations or in special local environments. But these reserves too become less stable under continued solar brightening. Snow cover declines, mountain glaciers retreat, and the seasonal timing of meltwater shifts. Surface water becomes more temporary, more uneven, and more vulnerable to loss. Earth in this stage is still a blue world from a distance, but less securely so than before. Its clouds still move, its oceans still reflect sunlight, and its storms still rise from warm seas. Yet the water cycle has begun to turn against its own long continuity. More water leaves the surface, more enters the air, and a small but persistent fraction begins the journey toward permanent escape. Lakes contract, dry regions expand, and the oceans start their very slow retreat. Liquid water remains present across the planet, but it no longer rests in the stable abundance that once defined Earth so completely. The surface of Earth supports a thin, active layer of life spread across land and shallow water. This living layer depends on sunlight, liquid water, suitable temperatures, nutrients, and gases in the atmosphere. In the long future, as the sun grows brighter and climate stability weakens, this living surface begins to fail. The change is not uniform, and it does not happen in a single moment. Forests, grasslands, wetlands, soils, and the countless small systems within them decline at different rates in different regions. Yet the general direction is clear. The broad, productive skin of life on the continents and in sunlit waters becomes steadily harder to maintain. A central reason is carbon dioxide. Plants, algae, and many microbes use carbon dioxide in photosynthesis, the process by which light energy drives the building of organic matter from carbon dioxide and water. This process also releases oxygen. On the modern Earth, the concentration of carbon dioxide in the air is low compared with some distant past eras, but it is still high enough for widespread plant growth. In the future described here, long-term weathering continues to draw carbon dioxide downward while the sun continues to brighten. This combination places life in a narrowing interval. There is more sunlight, but the gas needed to turn that light into stored chemical energy becomes scarce. Photosynthesis does not fail all at once for every organism. Different plants use different pathways. Some are better suited to hot, dry conditions. A well-known example is the group called C4 plants, which concentrate carbon dioxide inside their tissues and can continue functioning at lower atmospheric levels than many other plants. Even these more efficient forms have limits. As carbon dioxide falls over geological time, many familiar plants lose efficiency, grow more slowly, and struggle to maintain water balance. Their pores, called stomata, must open to take in carbon dioxide, but open pores also allow water to escape. In hotter, drier air, this trade becomes increasingly severe. A plant cannot easily keep both enough carbon and enough water. Heat adds another pressure. Every organism has a range of temperature within which its enzymes and membranes function well. Enzymes are molecules that help chemical reactions proceed. When temperatures move too far above the usual range, proteins lose shape. Membranes become unstable. and photosynthesis becomes less efficient. Leaves can overheat in direct sunlight, especially when evaporative cooling weakens because water is scarce. Roots in dry soil cannot replace lost moisture fast enough. Even before absolute thermal limits are reached, daily stress accumulates, growth slows, reproduction falls, and recovery from damage becomes harder. Rainfall also becomes less reliable across many landscapes. A warmer climate can still produce intense rainfall in some places, but the broader land surface loses the steady availability of moisture that supports large ecosystems. Forests depend not only on total yearly rain but also on its timing, on soil storage, on humidity, and on moderate temperature. When dry seasons lengthen and heat strengthens, forests thin. Tree death opens the canopy. More sunlight strikes the ground. Soil moisture declines more quickly, and fire risk rises where enough vegetation remains to burn. Fire is already a natural part of many ecosystems, but in a hotter and less stable future, it can become more destructive and less balanced by regrowth. Grasslands and shrublands may persist longer in some regions because they can tolerate seasonal dryness better than dense forests. Yet they too depend on a minimum supply of water and carbon dioxide. As those supports weaken, plant cover becomes patchier, bare ground expands. Soils, once held in place by roots and protected by leaf litter, are exposed to wind and intense rain when it comes. Erosion increases in some places, while hard crusts form in others. The biological richness of the land declines not only in large visible species but also in fungi, insects, worms, and microbes that recycle organic matter and maintain soil structure. The oceans near the surface also lose part of their living skin. Phytoplankton, the microscopic drifting organisms that perform much of the ocean's photosynthesis, depend on light, nutrients, and chemical conditions in the water. Their future is shaped by warming, changing circulation, and the gradual decline of Earth's overall habitability. In this section, the attention remains on the broad surface biosphere rather than on later, more isolated refuges. The key point is that the sunlit zone of the life, on land and in shallow waters, becomes less productive as the physical setting moves away from the conditions under which large ecosystems thrive. Animals depend on plants directly or indirectly. As plant productivity declines, food webs contract, large herbivores lose forage, predators lose prey, pollinators decline with flowering plants, scavengers and decomposers lose the regular abundance of organic matter that once flowed through ecosystems. Heat itself places additional stress on animals because body temperature, water balance, and breeding cycles all depend on climate. Many species can move for a time toward cooler latitudes, higher elevations, or wetter local environments. But the long-term trend removes these options one by one. Migration delays loss, but does not prevent it when the underlying planetary state continues to change. Oxygen in the atmosphere remains present for a long time because it is stored in enormous quantity compared with annual biological production. The decline of complex ecosystems does not mean immediate disappearance of breathable air. Still, over very long spans, the weakening of photosynthesis changes the balance between oxygen production and consumption. At the surface, this is first felt not as sudden atmospheric collapse but as ecological silence. Landscapes that were once noisy with growth, decay, and seasonal return become simpler and thinner in living cover. There is no single last forest or final grassland in a global sense. Different regions fail at different times, shaped by latitude, altitude, local water supply, and geology. Some cooler coasts may remain productive longer, some uplands may shelter moisture, Some hardy plant communities may hold on where conditions briefly allow, yet the overall pattern is one of retreat. The continents lose their continuous green cover and become increasingly broken into scattered zones of survival. The productive edge of shorelines shrinks as water chemistry and climate shift. Soils, no longer renewed by dense plant life, begin to behave more like mineral surfaces than living ground. Earth in this stage still has air, seas, clouds, and light. But the surface life that once softened the planet with roots, leaves, peat, and wood becomes sparse. The living skin grows thin, photosynthesis, which for so long ties sunlight to atmosphere and landscape, weakens under the combined force of low carbon dioxide, increasing heat and drying land. The surface remains active in wind and weather, but less active in growth. The continents begin to quiet, and the world of large ecosystems gradually gives way. After the broad surface biosphere declines, life does not vanish from Earth at once. The planet still contains water in some places, chemical gradients in rock and sediment, and isolated environments where temperatures remain within the range that some organisms can endure. The world is no longer covered by forests, grasslands, reefs, and rich coastal shallows. Instead, life contracts into scattered refuges. These are the last habitats of a living Earth, and they are occupied not by large animals or complex plant communities, but mainly by microbes adapted to heat, dryness, salt, or chemical scarcity. A microbe is a living thing too small to be seen without magnification. Bacteria and archaea belong to this world. They already live across modern Earth in hot springs, deep rock pores, salty lakes, acidic pools, and frozen ground. Their present existence shows that life can tolerate a much wider range of conditions than large surface organisms can. In Earth's future, this resilience becomes central. As the surface grows hotter and drier, the remaining biosphere is shaped less by sunlight and more by local shelter, moisture retention, and chemical opportunity. Shallow surface habitats disappear first across many regions because they are the most exposed. Thin soils dry out quickly. Seasonal pools vanish. Leaf litter and root networks no longer hold moisture near the ground. On open land, daily heating becomes severe, and without dense plant cover, the ground absorbs sunlight more directly. The surviving microbes therefore depend on places where water lingers or where rock provides a buffer against rapid swings in temperature. Cracks in stone, porous sediments, shaded cavities, and subsurface films of moisture become more important than open surfaces. Heat-tolerant organisms gain an advantage in these conditions. Some present-day microbes grow in waters hotter than those tolerated by plants or animals. They do this through proteins and membranes that remain stable at temperatures that would damage most familiar life. Yet even these organisms have limits. No known life remains active at unlimited heat. The last biosphere is therefore not a world of universal microbial endurance. It is a world in which only certain narrow environments continue to stay wet enough, cool enough, or chemically suitable enough for metabolism to continue. Hot springs and geothermal regions are among the possible refuges. These places are heated from below by Earth's internal energy, rather than only by the sun. Their chemistry can support microbial communities that draw energy from dissolved minerals and gases. Life of this kind does not rely entirely on sunlight. Some microbes use chemical energy by transferring electrons from one substance to another, a process similar in principle to respiration. In modern Earth, such communities exist around hydrothermal systems and in subsurface rocks. In the future, they may outlast surface ecosystems because they depend more on local geology than on the fading stability of the global climate. Salt-rich waters can also remain habitable for specialized organisms. As lakes shrink and seawater concentrates in isolated basins, salinity rises. Most organisms cannot tolerate very salty water because salt disturbs the balance of water across cell membranes. Some microbes, however, are adapted to such conditions. They maintain internal chemistry that prevents dehydration and allows metabolism to continue in brines that would kill most other life. These environments are harsh, but they may persist longer than fresher waters in arid landscapes because dissolved salts lower the freezing point and alter evaporation behavior. Even so, extreme salinity eventually becomes limiting, and only the most specialized forms remain. Rock itself offers protection. Just below the surface, pores and fractures can hold films of water long after exposed ground dries out. Mineral grains shade microbes from intense radiation. Temperature changes are also slower in rock than in open air. This subsurface zone may remain one of the most important final habitats. It is not deep in the sense of the mantle or the hot interior. It is a shallow hidden world of damp pores, chemical gradients, and low energy flow. The organisms living there work slowly. Their metabolism is faint compared with the productivity of ancient forests or oceans. Yet over long time they persist because they need little, and because their environment changes more gradually. The remaining microbial world is also shaped by the chemistry of water loss. As water becomes scarce, dissolved substances become more concentrated. Acidity may increase in some environments. Oxidation, the transfer of electrons that often involves oxygen, can alter minerals and organic remnants. Some microbes use these chemical changes as energy sources, while others are damaged by them. The late biosphere is therefore patchy not only in space, but also in chemistry. One spring, one basin, or one rock layer may support life, while a nearby environment with slightly different salt content, temperature, or acidity may be sterile. Sunlight still matters, but less widely than before. In open surface habitats, strong radiation and heat become more harmful than helpful for many organisms. A few photosynthetic microbes may survive in specialized settings where water remains shallow and conditions remain moderate enough. Mats of microbes can already live in modern hot springs and saline flats, forming layered communities where light reaches only the upper surface and chemistry changes millimeter by millimeter beneath. In the far future, such communities may represent some of the last direct use of sunlight by life on Earth. Their scale is small, their activity limited, and their continuity uncertain, but they show that the last biosphere need not be entirely dark. The amount of oxygen produced by these remnant communities is negligible compared with the ancient work of forests and plankton. The late biosphere no longer shapes the whole atmosphere in a strong way. Instead, it survives within conditions set by a planet that is becoming increasingly hostile. Life persists locally rather than globally. It no longer covers the Earth. It clings to specific waters, rocks, and mineral systems that hold a little of the old habitability for a little longer. It remains uncertain exactly which refuge would endure the longest, because that answer depends on the pace of solar brightening, the future state of the atmosphere, the survival of groundwater, and the changing chemistry of shrinking water bodies. Observations of modern extremophiles, meaning organisms that thrive in extreme environments, indicate that microbial life can remain active under conditions far harsher than those suited to complex organisms. It remains uncertain how long such life could continue as Earth loses more water and the atmosphere carries increasing heat. What is known is that the final living Earth is not a green world or a blue one in the familiar sense. It is a sparse microbial planet with life reduced to scattered refugees where water, rock, and chemistry still meet in the right proportions. The oceans remain the largest visible reservoir of water on Earth long after forests thin and large ecosystems withdraw. Their retreat is slow, but it leaves a clear physical record across the planet. As more water enters the atmosphere, as more hydrogen is gradually lost to space, and as evaporation continues to outpace secure long-term return, the sea begins to shrink basin by basin. This does not produce one uniform shoreline or one single moment of disappearance. Instead, the planet develops wide exposed shelves, isolated inland waters, increasing salinity, and expanding plains of mineral residue. Earth still holds great bodies of water during much of this interval, yet the character of the seas changes from open abundance toward concentration and retreat. An ocean basin is not a simple bowl. It is a vast irregular depression shaped by tectonic plates, volcanic ridges, trenches, continental shelves, and deep plains. Because of this uneven shape, a falling sea level reveals the margins first. Broad, shallow shelves around continents emerge before the deep centers are strongly affected. These shelves now hold many of the modern world's fisheries and coastal ecosystems, because sunlight reaches the water easily and nutrients circulate between land and sea. In the future, as the ocean edge withdraws, these shallow marine environments vanish across large distances. New coastlines form farther seaward from the old continental margins, while former seabeds dry under open sky. The newly exposed ground does not resemble ordinary land at first. Marine sediments cover many of these surfaces. Fine mud, carbonate deposits, shells, salts, and organic remnants lie across the shelves in thick layers. As water retreats, these sediments dry, crack, and are reworked by wind. In some places they harden into crusts. In others they break into dust. The sea leaves behind broad, flat expanses with little relief, interrupted by channels, stranded lagoons, and remnant basins where water still collects. These landscapes preserve the memory of former coasts through terraces, beach ridges, and old tidal forms, but now they stand motionless above the new shoreline. Salinity rises as ocean volume declines. Seawater contains dissolved salts delivered over immense time by weathering of continental rocks and by inputs from Earth's interior. When water evaporates, most of these salts remain behind. Present oceans are salty because this process has operated for a very long time, while water has stayed abundant enough to keep the salts diluted within a large volume. In a shrinking ocean, dilution weakens. The same dissolved load is held in less liquid water, and concentration increases. This change affects the physical behavior of seawater, including density, freezing point, and circulation. It also alters which minerals precipitate out as crystals when concentration becomes high enough. Different salts come out of solution at different stages. Calcium carbonate can precipitate under some conditions. Gypsum, a mineral containing calcium and sulfate, can form as concentration increases further. Halite, the mineral form of common salt, appears in more concentrated brines. Modern evaporate deposits, meaning layers of salts left behind by evaporating water, show that Earth has experienced enclosed basins with intense evaporation in the past. In the far future, such processes become widespread on a shrinking planet. Isolated seas and coastal basins may turn into evaporating pans, leaving thick mineral beds that record repeated wetting and drying. The chemistry of retreating oceans becomes more extreme. Brines, meaning waters with very high dissolved salt content, can persist where ordinary seawater once moved freely. These brines are denser and often settle in low basins. Their surface may gleam in strong light, while beneath them chemical conditions become harsh for most forms of life. Some microbes can endure such salinity, but the oceans as a broad connected habitat lose their former ecological character. The change is not simply from large to small, it is from chemically moderate to chemically concentrated. The seas no longer serve as a stable global medium in the way they once did. Circulation also changes as basins contract. Modern oceans move heat and dissolve substances through currents driven by wind, Earth's rotation, and differences in density caused by temperature and salinity. This circulation helps regulate climate and distribute nutrients. In a smaller, saltier ocean, the geometry of the basins changes and the forces that drive mixing operate on a different system. Shallow shelves disappear, straits close, and formerly connected waters become separated. Dense brines may sink quickly in some basins, while stratification, meaning layered water that resists mixing, can strengthen in others. The result is a less connected and less forgiving ocean. Former seafloors exposed to air begin to weather in unfamiliar ways. Sediments that formed underwater now meet wind, heat, and sparse rain. Carbonate muds can harden or dissolve depending on local chemistry. Salt crystals grow in pores and break rock apart. Fine grains are lifted by dry winds and carried inland or back toward the remaining shore. In low basins, thin transient lakes may form after rare rainfall, only to evaporate again and leave fresh mineral skins on the ground. The retreating sea creates landscapes that are both marine and continental in origin, belonging fully to neither. The deepest parts of the ocean persist the longest. Even after wide shelves are exposed and enclosed basins have concentrated into brines, the great abyssal plains still hold water. These deep regions are cold relative to the heated surface and contain immense volume. Their persistence gives the planet a final phase as a world of reduced but still present major seas. Yet the margins of those seas are unlike earlier coasts. Their shorelines may be steep where water now meets continental slopes. Their chemistry grows more concentrated. Their exchange with the atmosphere becomes increasingly loaded with evaporation and heat. Tides continue to work on the remaining water bodies, though their patterns shift with the shapes of the basins. Waves still break along shores, but the distances and depths over which they travel change. Sediment transport continues, though with less river input from a drier land. Deltas shrink or become inactive where rivers fail. Estuaries vanish where the balance between fresh water and seawater no longer exists. Coastal plains once renewed by tides, and rivers become abandoned surfaces, marked by channels that no longer carry regular flow. From a distant view, Earth loses some of the visual softness that oceans once gave it. Blue areas contract, bright salt flats and pale sediment plains expand. The sea remains, but it occupies less of the globe and carries a heavier load of dissolved minerals. The retreat is not only a loss of water from place to place, it is a redefinition of the planet's outer skin. Broad connected oceans give way to diminished basins, concentrated brines, and exposed marine floors. Water still gathers in the deepest hollows, but much of what was once covered by moving sea is left silent beneath a hotter sky. The continents remain after the seas retreat from many of their margins, but they no longer resemble the living surfaces known for most of Earth's recent history. Without dense plant cover, without steady soils rich in organic matter, and with a much weaker hydrological cycle, the land becomes more directly exposed to light, heat, wind, and mineral change. The outer face of the continents enters a quieter state in biological terms, yet a very active state in physical and chemical terms. Bare rock, dust, salts, and thin residual sediments begin to shape the appearance and behavior of the land more strongly than forests, rivers, or grasslands once do. Weathering continues, though its character changes. Weathering is the slow breakdown of rock at or near the surface through physical stress and chemical reaction. On the modern Earth, water is the great partner of weathering. Rain enters cracks, dissolves minerals, supports soil chemistry, and carries dissolved material downslope toward rivers and seas. Roots widen fractures. Organic acids from plants and microbes alter mineral grains. In the future dry world, much of this living contribution fades, and liquid water becomes less reliable across broad areas. Rock still changes, but it changes under a different balance of forces. Physical weathering grows important in exposed terrain. The daily cycle of heating and cooling places stress on the outer layers of rock. Sunlit surfaces expand in warmth, then contract as temperatures fall. Where moisture remains very low and vegetation no longer shades the ground. These swings can become more severe at the surface than deeper below. Over long periods, repeated expansion and contraction weaken rock faces and help outer layers flake away. In places where minerals have different rates of thermal expansion, grains pull against one another and small fractures multiply. This is a slow process, but on a continent left open to strong sunlight and large temperature contrasts, it becomes a persistent sculptor of the land. Salt also becomes a major agent of breakdown. As rare water films move through rock pores and then evaporate, dissolved salts crystallize. Growing crystals exert pressure on the surrounding mineral framework. This pressure can prise apart grains and widen tiny openings. On a drying planet, salt weathering becomes common in former coastal zones, exposed marine sediments, inland basins, and any place where groundwater rises near the surface and then evaporates. The rock does not need heavy rain to be damaged. It needs only intermittent moisture and dissolved salts. In this way, even a weakened hydrological cycle remains geologically effective. Chemical weathering does not disappear, but it becomes more selective. Water is still required for many mineral reactions, so in the driest regions chemical change slows greatly. Yet where groundwater lingers, where brief rains fall, or where humid air wets mineral surfaces, reactions continue. Iron-bearing minerals oxidize and form reddish coatings. Silicates alter into clays where enough moisture and time remain. Carbonates may dissolve during wet intervals and recrystallize during dry ones. The continents develop surfaces marked by thin varnishes, crusts, and alteration rims rather than thick living soils. Weathering becomes shallower in many places, acting on exposed outer zones rather than penetrating deeply through biologically active ground. Dust becomes one of the defining materials of the late continents. Fine particles are produced from dried lake beds, exposed shelf sediments, volcanic ash where volcanism remains active, and the mechanical breakdown of surface rock. Without vegetation to anchor the ground, wind lifts this material easily. Dust storms can move enormous volumes of fine mineral grains across open terrain. Some particles travel only a short distance and settle into hollows. Others remain suspended and are carried far across the continents. Over time, the land surface may be draped with shifting blankets of fine sediment, interrupted by stony pavements, where wind has removed smaller grains and left coarse fragments behind. These stony pavements form when loose fine material is steadily blown away and heavier fragments remain. The resulting surface can look ordered, almost arranged, even though it forms through long natural sorting. Such surfaces resist further erosion better than loose dust, so they can persist for long periods. Nearby, dunes may rise where wind deposits sand-sized grains. Sand differs from dust in grain size and motion. It moves by hopping along the surface under strong wind, building ridges and fields that shift gradually with changing airflow. On the silent continents, dune systems may expand into regions once held by soil, wetlands, or vegetation. The weakening of rivers changes the whole geometry of the land. Many valleys remain, cut during wetter ages, but only some continue to carry regular flow. Channels may lie dry for long intervals and then briefly fill during rare storms. Such events can still be powerful. Dry ground sheds water quickly because little vegetation or organic soil remains to absorb it. Flash floods can therefore sweep through valleys, move sediment, and then vanish, leaving the channel empty again. Over long time, the continents become shaped less by steady transport and more by episodic pulses of flow separated by long stillness. The colour of the land also changes. Green fades with the loss of plant cover, exposed rock, oxidized iron minerals, pale salts, and tan dust come to dominate. Former seafloors may appear white or light grey where evaporate minerals coat the surface. Old volcanic terrains may remain dark until weathering and dust soften them. Red and brown tones spread where oxidation alters iron-rich rocks. These colours are not decoration. They are signs of mineral chemistry operating in open air under strong radiation and limited moisture. Groundwater still matters even when it's hidden. Where water moves slowly through porous rock and emerges near the surface, it can cement sediments, deposit mineral crusts, or support brief local weathering zones. Some continental depressions may host transient brine ponds after rare rainfall or seepage. Their edges can accumulate layered salts and mud cracks, then return to dryness. These small features record the continuing but weakened presence of water in a land ruled mainly by heat and evaporation. The continents in this stage are not dead in a geological sense. They continue to fracture, oxidize, shed dust, and respond to wind. Their surfaces are reworked by mineral growth and breakdown. Yet they have become quieter because the living processes that once bound rock, water, and air together at the surface are greatly diminished. Soil no longer blankets the land in the old way. Broad root systems no longer hold slopes. Rivers no longer renew most lowlands with regular sediment and moisture. The exposed continents become worlds of crust, powder, salt, and stone, shaped by sparse water and persistent wind beneath an increasingly severe sky. Beneath the dust, salt, and exposed sediment of the continents lies the outer solid shell of Earth. This shell is the crust, the thin rocky skin that forms the upper part of the planet's rigid exterior. In the long future, after oceans retreat and surface life thins away, the crust remains under the same hotter sky that reshapes the land above it. The crust does not respond as quickly as air or water, yet it is not isolated from surface change. Heat entering from above, water disappearing from the surface, salts concentrating in basins, and the removal of vast masses of ocean water all influence how the outer ground behaves. The result is a crust that continues to fracture, settle, exchange gases with the atmosphere, and adjust to a changed planetary surface. The crust is made of different rock types formed in different ways. Some rocks crystallize from molten material. Some are built from fragments compacted into layers. Some are transformed by heat and pressure from earlier forms. At the surface, these rocks meet air and what remains of water. They expand and contract with temperature, crack under stress, and host slow chemical reactions within pores and fractures. In earlier ages, dense vegetation, active soils, and abundant water cover much of this crust with a living and mobile layer. In this later world, the covering is thinner, More bare stone is exposed directly to the atmosphere, and the crust becomes a more immediate participant in surface change. Heat from above matters because the near-surface part of the crust responds to repeated warming. Rocks are not good at adjusting instantly to temperature shifts through their full thickness. The outermost part warms fastest, while deeper material changes more slowly. This difference creates internal stress. Over long periods, sheets of rock can peel, blocks can separate along natural joints, and surfaces can become broken into angular debris. This process is strongest where skies remain clear. Moisture is low, and daytime heating is intense. The hotter air above the land does not melt the crust, but it changes the rate and style of its breakdown near the surface. The loss of water from the surface also changes the weight pressing down on the crust. Oceans are heavy, ice is heavy. Groundwater stored in pores and sediments also adds mass. When these reservoirs shrink, the crust adjusts. Such adjustment is called isostatic response, which means the slow rising or sinking of Earth's outer shell as loads are added or removed. Modern examples can be seen where land still rises after large ice sheets have melted away. In Earth's future, the gradual loss of surface water alters loading on a planetary scale. The response is uneven because water is not removed equally everywhere and because crustal thickness varies from place to place. Some regions may rise slightly over immense spans, while others respond more weakly. This motion is slow, but it changes slopes, basin depths, and the paths along which water or sediment can move. Cracks and faults in the crust remain important. A fault is a fracture along which blocks of rock move relative to one another. Some faults are large and tied to plate motion, while others are smaller features in continental interiors in the hotter, drier future. Many old cracks widen near the surface because of thermal stress and salt growth. Rare floodwater can enter them, deposit minerals, and then vanish. Some fractures become pathways for the last groundwater. Others become filled and sealed by precipitated salts, silica, or carbonates. The near-surface crust is therefore not merely breaking apart. It is also recording chemical traces of the new environment within its openings. Gas exchange between crust and atmosphere continues. Rocks contain carbon, sulfur, and many reactive minerals. When they weather, they can consume or release gases depending on the material and conditions. In earlier climatic stability, silicate weathering removes carbon dioxide over long time. In the hotter future, that process still occurs where water and reactive rock meet, but it operates under stricter limits because widespread moisture is reduced. Carbonate rocks may also break down or reform depending on local temperature, moisture, and acidity. In exposed basins, repeated wetting and drying can leave crusts of evaporate minerals. These are not only surface decorations, they represent material brought upward in solution and fixed into solid form by evaporation. The drying of the crust's upper layers affects how water moves through them. When soils are rich and organic matter is abundant, rainfall can be absorbed gradually. In the later dry world, many surfaces become hard, sealed, or sparsely fractured. Water then runs off quickly during rare storms or sinks only through specific openings. Recharge of aquifers becomes less regular. Some shallow stores disappear entirely. This means that the top of the crust becomes more sharply divided between dry zones and the few channels or fractures that still carry moisture downward. Chemical reactions become concentrated along these limited pathways. A great deal of the exposed crust remains nearly inactive in terms of liquid water, while a small fraction hosts the final local exchanges between water, air, and stone. Sedimentary basins respond in their own way. These are regions where layers of sediment accumulate over time. When seas retreat and rivers weaken, the supply of new sediment changes, but dust and salts continue to enter some basins. In enclosed lowlands, evaporation can leave thick mineral layers. These added deposits load the local crust even as loss of water unloads it. The pattern becomes complex. One basin may fill with dry sediment and salt while a nearby region rises slightly after water loss. Over immense spans, such changes alter the arrangement of continental surfaces without changing the fact that the overall crust remains rigid compared with the softer layers below. Volcanic gases may still reach the atmosphere through active regions, adding carbon dioxide, water vapor, sulfur gases, and other compounds. The amount varies with tectonic activity, which continues on its own deeper timescale. At the crustal level, this means some parts of the surface remain connected to deeper reservoirs through vents, geothermal systems, and young igneous rock. These areas may host stronger mineral alteration because hot fluids react quickly with surrounding stone. In the broader dry setting, they stand out as rare places where crustal chemistry remains vigorous. The crust under a hotter sky is therefore not passive. It expands and fractures at the surface, adjusts slowly to changing loads, channels the last groundwater through narrowing pathways, and continues its long exchange of minerals and gases with the atmosphere. It preserves traces of vanished oceans in exposed marine sediments and traces of rare water in salts and veins. The outer ground of Earth becomes harder, barer, and more chemically selective. It remains the interface between the open planet above and the deeper interior below, shaped now less by life and flowing water than by heat, dryness, mineral concentration, and the slow mechanical response of stone. Within the crust, far below the dry plains and exposed shelves, large amounts of carbon remain locked in stone. This carbon is not part of the thin living layer that once moves quickly through leaves, soils, and air. It belongs to the slow geological store built across immense spans of time. Shells, skeletons, buried organic matter, altered sediments, and mineral reactions have placed carbon into limestone, dolostone, shale, coal, oil-bearing rock, natural gas deposits, and deep crustal fluids. In Earth's future, after the surface climate loses much of its familiar stability, this buried carbon still matters. It no longer supports a rich biosphere above, but it remains part of the long exchange between the atmosphere and the solid planet. Carbon in rock takes several main forms. One is carbonate carbon, held in minerals made from carbon and oxygen joined with metals such as calcium or magnesium. Limestone is the best-known example. Another is reduced carbon, meaning carbon in a more energy-rich state, as found in buried organic matter and fossil fuels. These forms are created under different conditions and released through different processes. On the surface, carbon dioxide can dissolve in water, react with weathered minerals, and eventually be stored in marine sediments as carbonate. Organic carbon can be buried when dead material escapes full decay. With time, pressure, and heat, this material can be altered and preserved within the crust. Together, these stores hold far more carbon than the atmosphere does. In the long future, the surface air contains less carbon dioxide than it does today, because weathering has slowly drawn it down while the sun continues to brighten. This means the crust becomes even more important as the main long-term carbon reservoir. Yet storage is only one part of the story. The crust also releases carbon, and this release continues through metamorphism, volcanism, and thermal breakdown. Metamorphism is the change of a rock under heat and pressure without full melting. When carbonate rocks or carbon-rich sediments are buried, heated, and compressed, Some of their carbon can be driven out in fluids or gases, including carbon dioxide and methane. These substances can then move upward through fractures or be released later by volcanic processes. This deep carbon cycle is slow. It does not operate on seasonal or even ordinary geological timescales. Carbon may remain in a buried rock for tens of millions or hundreds of millions of years before it is returned to the atmosphere or transferred deeper into the planet. In earlier ages, this slow return helps balance the removal of carbon dioxide by weathering. In the hotter future, the same exchange still exists, but the balance shifts. Weathering on dry continents becomes more limited by lack of water, even while low atmospheric carbon dioxide leaves less room for further drawdown. Volcanic and metamorphic release therefore may become proportionally more important in maintaining whatever carbon dioxide remains in the air. The distribution of carbon-bearing rocks across the crust is uneven. Ancient shallow seas leave thick carbonate platforms on some continents. Deep sedimentary basins preserve organic-rich muds in others. Mountain belts expose rocks that were once buried far below the surface, including carbon-bearing layers that now weather in the open air. As continents dry and old seafloors are exposed, many of these rocks lie closer to the surface than before. This does not mean they release their carbon rapidly. Most remain stable unless heated, dissolved, fractured, or chemically altered. Even so, the future surface environment changes the conditions under which shallow carbon-bearing rocks interact with air and the remaining water. Carbonate rocks are especially widespread. They form in many marine environments when organisms or chemical processes produce calcium carbonate and related minerals. Over time, these materials compact into stone. In the future dry world, carbonate rocks on land may experience cycles of dissolution and recrystallization where rare moisture persists. In most arid settings, however, their weathering becomes slower because liquid water is scarce. Large carbonate masses may therefore remain exposed for long intervals, pale and reflective under strong sunlight. Their presence affects the chemistry of local water when water appears. But their main role in the global story is as a long-term carbon store waiting on deeper geological processes. Organic carbon in the crust behaves differently. Coal beds, oil-bearing shales, and natural gas accumulations represent ancient biological productivity, buried and altered over time. Near the surface, if these materials are exposed to oxygen and enough heat, they can slowly oxidize. In the deep crust, further burial and warming can convert one form to another or release gases into pore spaces and fractures. On the future Earth, widespread burning of such deposits by human industry is no longer part of the planetary system under discussion. What remains relevant is natural geological release, heat from burial, pressure from overlying rock, and movement along faults can all mobilize reduced carbon and send part of it upward. The changing surface load from shrinking oceans and drying basins may also influence fluid movement in the crust. When weight is removed from the surface, pressure conditions in sedimentary basins and fracture systems can shift. These changes are slow and subtle, but they can alter the paths along which fluids migrate. Carbon-bearing fluids may move through permeable layers, collect beneath seals, or escape through faults where crustal stress opens new pathways. In some places, carbon dioxide may dissolve into groundwater or brines and later precipitate as carbonate again. In others, it may vent gradually into the atmosphere. The carbon cycle in stone is therefore not only a matter of storage and release, it also includes movement, temporary trapping, and remineralization. Heat matters throughout this deeper story. The crust warms with depth because Earth's interior remains hot from its formation and from radioactive decay. This geothermal gradient, meaning the increase of temperature with depth, controls when organic matter matures into hydrocarbons, when carbonates react under metamorphism, and when fluids become mobile enough to carry dissolved carbon through rock. In a future with hotter surface conditions, the upper boundary of this gradient is shifted slightly, but the deep pattern is still dominated by internal heat. The crust remains a zone where surface history and interior energy meet. Carbon stored there is part of both worlds. The slow release of carbon from stone does not restore the old climate balance. The sun continues to brighten, and the conditions that support the former biosphere do not return. Still, deep carbon helps determine the composition of the remaining atmosphere. Even a thin future atmosphere is shaped by the gases that geology continues to supply. Carbon dioxide may remain low, but it is not erased entirely because Earth's interior and crust continue to return carbon upward across immense spans. Methane, when released, may not remain long in an oxidizing atmosphere, yet it too can play a role locally and briefly. What matters most is that the crust still breathes carbon on its own slow schedule. Beneath the silent continents, deep carbon in stone endures as the memory of ancient seas, ancient forests, ancient plankton blooms, and ancient burial. It is the long archive of a once living planet written into mineral and sediment. In Earth's strange future, this archive remains active in a restrained way. Carbon moves downward no longer with the same richness of surface life, yet it still rises from depth through heat, pressure, and fracture. The climate above has drifted away from its former balance, but within the crust the old planetary exchange continues, reduced in speed, spread across stone, and governed by the immense patience of geological time. Below the crust lies the mantle, a vast rocky layer that occupies most of Earth's volume. It is solid on short timescales, yet over immense spans it flows slowly enough to behave like a very stiff fluid. This slow movement carries heat from the deep interior toward the surface and helps drive plate tectonics. The long-term motion of Earth's outer rigid plates, in the far future, even as the surface becomes drier, hotter, and less hospitable, the mantle continues its work beneath it. The continents above may lose forests, rivers, and stable seas, but the deeper engine of the planet does not stop simply because the surface climate changes. The mantle follows its own timescale, slower than weather, slower than oceans, and even slower than the decline of the biosphere. The mantle is made mainly of silicate rock rich in magnesium and iron. Pressure increases strongly with depth, and the minerals inside the mantle change their structure in response. These changes divide the mantle into broad zones, yet all of them remain part of one connected thermal system. Heat inside Earth comes from two main sources. One is leftover heat from the planet's formation, when collisions and compression warmed the young Earth. The other is radioactive decay, the gradual breakdown of unstable atoms within the interior that releases energy. Together these sources keep the mantle hot enough to convect. Convection is the slow circulation of material driven by differences in temperature and density. Hotter rock tends to become more buoyant and rise, while cooler rock becomes denser and sinks. This motion is extremely slow. Mantle rock does not rush like water in a river. It creeps over millions of years. Even so, that creeping motion is powerful enough to reshape the surface through mountain building, seafloor spreading, subduction, and volcanism. In the future world above, the surface may look silent and exhausted, but beneath it the mantle remains active. Some plates continue to move, some ocean basins continue to open or close. Some regions still carry crust downward into the deep earth, while other regions bring hot material upward toward ridges or volcanic provinces. The connection between mantle motion and surface conditions becomes quieter, but it does not disappear. Plate tectonics helps recycle rock, water, and carbon between Earth's outer shell and interior, when oceanic crust sinks into the mantle at subduction zones. It carries minerals, sediments, and sometimes water bound within rocks. When mantle material rises and melts, it can produce magma, which may later reach the surface as lava or solidify within the crust. Volcanic gases released from these processes continue to supply carbon dioxide, water vapor, sulfur compounds, and other gases to the atmosphere. In the future Earth, this geological outgassing remains one of the few large-scale ways in which the planet's interior still affects the air above. The mantle also changes with time. Earth slowly cools as it loses heat into space. This cooling does not happen quickly, and it does not end tectonic activity in the near future on astronomical timescales relevant to the sun's brightening. Yet the long trend matters. A cooler mantle becomes less vigorous in convection, and this may reduce tectonic speeds over immense spans. Observations of Earth today and comparisons with other rocky planets suggest that internal cooling can alter how efficiently a planet renews its surface. It remains uncertain exactly how plate tectonics will evolve in Earth's far future, because that depends on mantle temperature, water content, lithosphere strength, and the continuing arrangement of continents and ocean basins. What is known is that mantle convection is robust on billion-year timescales, and it is likely to continue far into the era when surface habitability is already greatly reduced. Water plays an important part here, even at depth. The mantle is not full of open liquid water, but some minerals can store hydrogen within their crystal structure. Water also affects melting and rock strength. In subduction zones, water released from descending slabs lowers the melting point of surrounding mantle rock, helping magma form. If surface oceans shrink greatly and subduction patterns change, the long-term cycling of water into the mantle may also change. Less water available at the surface means less water eventually bound into newly formed oceanic crust, and less carried downward over time. This would slowly alter how the mantle and crust exchange volatile substances, though the response would unfold across very long intervals and would not erase the large amount already stored in Earth's mineral systems. The lithosphere, which is the rigid outer shell made of crust plus the uppermost mantle, rides above deeper, weaker mantle regions. Its plates crack, collide, separate, and slide past one another. In the future, these motions still create mountains and basins, though the surface environments that act upon them are different. A newly uplifted mountain range under a dry, hot sky weathers differently from one under forests and glaciers. A rift valley forming in a planet with retreating seas feels differently from one connected to active oceans. The mantle still produces the broad architecture of the surface, but the details of erosion, sediment transport, and climate interaction have changed. Hot rising mantle can also create mantle plumes, columns of unusually warm rock that rise from depth and may feed long-lived volcanic centers. Such plumes have been proposed beneath regions like Hawaii and Iceland in the present Earth. In the future, if plume activity continues, it may maintain isolated volcanic islands, basalt plateaus, or geothermal provinces. These regions could remain among the few places where the surface still receives concentrated heat and new rock directly from the interior. They also continue to release gases and shape local crustal chemistry. Even on a fading surface world, the mantle can still deliver local renewal. The deeper mantle remains beyond direct human observation, so knowledge comes from seismic waves, laboratory experiments, theoretical models, and the chemistry of volcanic rocks. Seismic waves change speed as they pass through different materials, allowing the structure of the mantle to be inferred. These methods show a layered yet convecting interior, with cold slabs descending in some places and hotter material rising in others. This picture remains the best scientific foundation for understanding Earth's internal future. The hotter sky above does not stop seismic waves, and it does not halt mantle circulation. The outer world may dry and empty, but the inner rocky body continues to move. The pace of mantle change is so slow that it gives the planet a kind of hidden continuity. Long after surface ecosystems collapse, long after the oceans begin their retreat, the mantle still carries heat upward. It still pushes and pulls the plates. It still helps maintain volcanism, mountain building, and deep recycling. The surface may no longer support the rich interplay of life, water, and air that once covered the world. Yet the deeper Earth remains geologically alive. In this way, the mantle preserves a different version of planetary persistence. It does not preserve habitability in the surface sense. It preserves motion, heat transfer, and material exchange. Beneath the rigid shell, rock still rises and sinks in darkness, driven by the energy of formation and decay. Earth's outer face becomes harsher and quieter, but the mantle beneath it continues its immense slow circulation, largely indifferent to the fate of clouds, forests, and seas above. Deeper than the mantle lies the core, divided into a liquid outer core and a solid inner core. This hidden region is made chiefly of iron with a smaller amount of nickel and lighter elements. It cannot be seen directly, yet its presence is known from the way seismic waves travel through Earth and from the behavior of the magnetic field around the planet. In the far future, when the surface has become hotter, drier, and less welcoming to life, the core continues to shape one of the most important invisible features of Earth. It powers the magnetic field, and that field still extends outward into space as a shield against part of the solar wind and high-energy charged particles. The outer core is liquid because temperature and pressure there allow iron-rich material to flow. The inner core is solid because the pressure at the center is so great that it forces the iron into a solid state despite the high temperature. Between these two regions, heat moves outward from deeper Earth into the lower mantle. This flow of heat helps drive motion in the liquid outer core. The motion is not random. Earth rotates, and rotation helps organize the moving metal into patterns that can generate and maintain a magnetic field. This process is called the geodynamo. A dynamo is a system in which motion in an electrically conducting fluid creates magnetic fields and helps sustain them. The magnetic field reaches far beyond the atmosphere. It forms a magnetic cavity in the stream of charged particles flowing outward from the sun. This stream is called the solar wind. Without a magnetic field, the solar wind would interact more directly with the upper atmosphere, transferring energy and stripping charged particles from high altitudes more effectively. A magnetic field does not stop all loss of atmospheric particles, and it does not create perfect protection, even today. Some particles escape from Earth's upper atmosphere, and some solar particles enter near the polar regions. Still, the magnetic field changes the way the atmosphere meets space. It deflects much of the incoming charged flow and helps preserve the overall structure of Earth's near-space environment. In the future Earth, this shielding remains significant because the atmosphere above is under increasing stress from a brighter sun. Higher solar energy warms the upper atmosphere, drives more photochemistry, and helps hydrogen escape from water molecules broken apart at high altitude. The magnetic field does not prevent sunlight from reaching the atmosphere, and it does not stop ordinary thermal escape of the lightest gases. Its role is different. It reduces some of the direct interaction between the solar wind and the upper atmospheric particles, especially ions, which are atoms or molecules carrying electric charge. In this way, the core continues to provide a degree of protection even when surface conditions have already moved far from their earlier balance. The field itself is not fixed. Earth's magnetic field changes in strength and structure over time. It drifts, develops irregular patches, and sometimes reverses polarity, meaning the magnetic north and south orientations switch. Geological records in volcanic rocks and sediments show that many reversals have happened in the past. These reversals do not mean the core stops working. They indicate that the geodynamo is dynamic and complex. During a reversal, the field can weaken and become more disordered for a time, but it usually remains present in some form. In the far future, similar variability is expected as long as the core remains convecting and electrically active. The exact timing of reversals cannot be predicted far ahead, but the existence of continuing change is well supported. The long-term survival of the magnetic field depends on energy sources within the core. One source is cooling. As Earth slowly loses heat to space, heat flows out of the core into the mantle. This helps drive convection in the liquid outer core. Another source comes from the growth of the solid inner core. As iron freezes onto the inner core, it releases latent heat, which is energy given off during a change of state. It also leaves lighter elements behind in the liquid outer core. These lighter materials are more buoyant and help sustain motion. Together, these effects support the geodynamo. Earth is still in this active phase today, and scientific understanding indicates that it should continue for a very long time. The eventual weakening or loss of the field would likely require much greater internal cooling over intervals, longer than the stages of solar brightening that dominate the future of surface habitability. This means that the core's magnetic shield may outlast the familiar biosphere. Surface ecosystems can collapse while the geodynamo continues below. Oceans can shrink while the liquid outer core still circulates. The surface may no longer be a place of forests, rivers, and abundant rain. Yet the planet can still carry an invisible magnetic structure around itself. This separation of timescales is part of what makes Earth's future strange. The outer world becomes less habitable because of the sun and the changing atmosphere, while the deep interior still behaves like that of a geologically active planet. The magnetic field also creates belts of trapped charged particles around Earth. These zones, shaped by the field and by incoming solar particles, form part of the planet's radiation environment in space. In a future with a brighter sun, solar activity may interact with this magnetosphere under stronger average input of energy. Though the detailed long-term behavior of the sun's magnetic activity remains more difficult to project than the steady increase in its luminosity. Observations of sun-like stars indicate general patterns, but exact future solar wind conditions and activity cycles remain uncertain across immense spans. What remains clear is that as long as Earth maintains a strong internal field, the basic magnetic shielding structure can still exist. Inside the core, motion is driven by forces and materials far removed from the dry continents above. Temperatures are immense, pressures are immense, iron-rich liquid circulates in darkness. The surface climate, even in its most altered future state, does not directly disturb this deep motion. The link between surface and core is indirect, mainly through the planet's long-term heat loss. That link is real but slow. A hotter sky does not turn off the dynamo. A retreating ocean does not end convection in liquid metal. The core follows its own internal schedule. The field produced by this hidden engine is therefore one of the last planetary systems still acting in a familiar way, while so much else has changed. It remains uncertain how its exact strength will vary at any particular future time, because magnetic behavior is naturally variable and reversal intervals are irregular. It is not uncertain that the core continues to matter. The geodynamo is a deep planetary process that helps define Earth as more than a bare rock. It gives the planet a magnetic presence in space, a moving shield shaped by flowing metal at great depth. Beneath the silent crust and the slowly convecting mantle, the liquid outer core continues to circulate around the solid inner core. From that motion, the magnetic field endures. It does not rescue the surface from the long consequences of a brightening sun, but it preserves one more layer of Earth's identity. Even as the world above grows harsher, the hidden engine below still turns, and the shield it creates still surrounds the planet in the dark space beyond the air. Earth circles the Sun along an orbit that is stable over ordinary human timescales, yet not perfectly fixed over the longer spans. The shape of the orbit changes slightly. The tilt of Earth's axis changes slowly. The direction in which that axis points also shifts. These motions alter the seasonal and latitudinal distribution of sunlight, and they have influenced climate throughout the planet's history. In the far future, however, these familiar orbital rhythms no longer serve as the main frame of change. The larger fact is simpler and stronger. The sun steadily brightens, and Earth remains in the same general region around it. The planet's place in space, once comfortably suited to long-lived surface oceans and widespread life, gradually becomes less favourable. A useful scientific idea here is the habitable zone. This term refers to the range of distances from a star where a rocky planet with suitable atmospheric conditions can maintain liquid water at its surface. It is not a sharp boundary like a wall. It is a range shaped by the brightness of the star, the reflectivity of the planet, the composition of the atmosphere, and the way water and clouds behave. A planet can be inside this range and still be uninhabitable for other reasons. A planet can also move toward the edge of the range without changing its distance from the star, simply because the star changes. That is Earth's situation in the long future. The orbit remains broadly similar, but the sun becomes more luminous, so the habitable zone moves outward. This outward shift happens very slowly. For immense spans, Earth still lies near the inner part of the sun's habitable region, and then gradually crosses beyond the conditions that allow long-term surface water stability. The key idea is not motion of Earth through space in a dramatic sense. It is motion of the climatic boundary relative to Earth's orbit. A planet that once receives the right balance of energy later receives too much. Its old feedbacks try to compensate. Reflective clouds. Rock weathering or a greenhouse adjustment, and the heat capacity of the oceans all play their part. Yet these forms of adjustment have limits, and Earth approaches those limits while still following its same annual path. Orbital shape matters because a more elliptical orbit changes how much sunlight reaches Earth at different points in the year. A circular orbit gives more even solar input. A slightly stretched one increases seasonal contrast between the closest and farthest points from the sun. Earth's eccentricity, meaning the degree to which its orbit departs from a perfect circle, changes slowly through gravitational interactions with other planets. These changes affect climate patterns, but in the far future their importance is secondary beside the steady rise in solar luminosity. The same is true for axial tilt. Greater tilt can intensify seasons, especially at high latitudes, while lower tilt reduces that contrast. In a world already moving beyond long-term surface habitability, such variations still influence where heat is distributed, but they do not restore lost planetary balance. The gravitational arrangement of the solar system remains another part of the story. Earth does not travel alone around the Sun. It is perturbed gently by the pull of Jupiter, Venus, Saturn, and the other planets. These interactions can alter orbital elements over long intervals, yet the solar system is dynamically stable enough that Earth is not expected to be suddenly thrown into a radically different path during the main stages of solar brightening described here. There are uncertainties in exact orbital evolution over extremely long times, because chaotic behavior exists in parts of planetary motion. Chaos in this scientific sense means that tiny differences can grow large over time, making very distant precise prediction difficult. Even so, the broad expectation remains firm. Earth continues near roughly its present distance while the Sun's output rises. Some processes can nudge the orbit slightly outward. As the Sun evolves, it loses a small amount of mass through the solar wind and later more substantial mass in advanced stages of stellar evolution. When a star loses mass, the orbits of planets can expand because the gravitational grip weakens. Before the Sun becomes a red giant, this effect is present but modest. It does not offset the rise in luminosity during the long era in which Earth first loses climate stability and surface water security. Later, during more advanced solar evolution, orbital expansion becomes more significant, though by then the Sun itself changes so profoundly that the earlier concept of a stable habitable zone becomes less useful. In the stage considered here, Earth cannot rely on outward drift to remain comfortable. The atmosphere is part of orbital limits as much as the orbit itself. A planet closer to the inner edge of the habitable zone can sometimes remain temperate if it reflects enough light or maintains the right balance of gases. A planet farther out may stay warm if greenhouse trapping is strong enough. Earth's problem is that the long-term decline of carbon dioxide reduces one source of adjustment, while water vapor feedback strengthens another. The orbit alone does not define the future. It sets the incoming energy level, while the atmosphere determines how that energy is handled. By this stage, the combination of brighter sunlight and weakened climatic flexibility means that Earth can no longer maintain the surface conditions that once made it a stable ocean world. Comparisons with Venus and Mars help clarify this point. Venus lies closer to the Sun and receives far more solar energy. It has a dense carbon dioxide atmosphere and a surface hot enough to rule out liquid water. Mars lies farther out and is much colder. With a thin atmosphere and little stable surface water today, Earth has long stood between these worlds in a more moderate state. In the far future, as the habitable zone moves outward, Earth ceases to occupy that middle balance. It does not become an exact copy of Venus, because planetary histories, sizes, atmospheres, and geological paths differ. Yet it moves away from the conditions that once distinguished it as a persistently wet and biologically rich planet. Latitude still matters during this interval. Equatorial regions receive more direct sunlight on average, while high latitudes receive less. Mountains, basin geometry, and remaining seas create local contrasts. Some regions remain more sheltered than others for a time. Still, this is local variation inside a global shift. Orbital mechanics can redistribute energy across seasons and latitudes, but they cannot erase the overall increase in solar input. The planet's path continues. The year continues, and the sky still changes with the seasons. Yet the old climatic meaning of those cycles grows fainter. The deeper lesson of Earth's orbital limits is quiet and exact. Habitability is not guaranteed by distance alone. It depends on the balance between a star's brightness and a planet's capacity to respond. Earth spends a very long time within a favourable interval, but the interval itself is not permanent. The Sun slowly changes. The habitable zone moves outward, and Earth remains near the same track. Its orbital rhythms continue, but they are carried inside a larger change that they cannot overcome. In this way, Earth's future in space is defined not by wandering away from the Sun, but by staying near a star that becomes steadily more luminous. The orbit remains orderly. The seasons still rise and fall according to tilt and motion. Planetary gravity still shapes slow variations in path, yet the wider celestial setting becomes less forgiving. Earth approaches and then passes the inner climatic limits of long-term surface habitability, not through sudden violence, but through the steady logic of stellar evolution and orbital persistence. The Sun does not remain in its present state forever. After spending most of its life steadily fusing hydrogen in its core, it enters a later phase in which the core runs out of ordinary hydrogen fuel. This is not a sudden event in any human sense. It unfolds across immense spans of time, yet in stellar terms it marks a profound change. The core, now made mostly of helium, no longer produces the same outward pressure from hydrogen fusion at its center. Gravity then causes the core to contract. As it contracts, it grows hotter. Hydrogen fusion continues for a time in a shell surrounding the helium core, and the energy released from this shell causes the Sun's outer layers to expand. The star becomes a red giant. A red giant is a star with a swollen outer envelope and a much larger radius than before. Its surface becomes cooler than the present Sun's surface, which is why it appears redder in colour, but its total energy output becomes far greater because its surface area increases so much. The Sun in this phase no longer resembles the compact yellow star that supports modern Earth. It becomes larger, more luminous, and more unstable in its outer structure. Earth's future under this transformed star is shaped first by light and heat, and then by the changing gravitational and physical relationship between planet and star. Long before the Sun reaches its greatest red giant size, Earth has already become deeply altered. The atmosphere has changed, the oceans have diminished, and the biosphere has largely vanished or contracted into narrow refuges. In this section, however, the focus remains on the Sun's late expansion itself and on the direct consequences for Earth as a planet orbiting ever closer, in relative terms, to a star that is no longer in quiet middle age. The key fact is simple. The energy Earth receives rises far beyond the level that allows any familiar surface condition to persist. As solar luminosity climbs during red giant evolution, Earth's surface is driven into extreme heat. Rock exposed at the surface absorbs a much stronger radiant flux. Any remaining water at or near the surface is lost. The atmosphere becomes dominated by the consequences of high temperature, chemical dissociation, and escape. Silicate materials at the surface, once stable under ordinary conditions, begin to behave differently under intense heating. Some minerals break down, some melt locally, and some release volatile components that had remained bound within them. The distinction between air, surface, and shallow crust becomes less neat because heat penetrates deeper into the outermost layers of the planet. The Sun's outer layers also become more diffuse as the star expands. Its mass is not held as tightly as before, and it loses material through a stronger stellar wind. A stellar wind is a flow of particles moving outward from the star, as the Sun loses mass. Earth's orbit can expand somewhat because the weakened gravitational pull allows the planet to drift outward. This effect is important and well supported by stellar physics. It means that Earth does not simply remain at its present orbital distance while the Sun swells around it. The planet moves outward to some degree, yet this outward drift may not be enough to guarantee survival as a separate intact world. A major uncertainty in Earth's final orbital fate comes from tidal interaction. Tides are not limited to oceans. They also arise whenever gravity pulls more strongly on one side of a body than the other, deforming its shape slightly and exchanging energy and angular momentum. As the Sun becomes a giant with an extended outer envelope, tidal forces between the swollen Sun and Earth may grow important. These forces can draw Earth inward relative to the outward effect of solar mass loss. Different models reach somewhat different outcomes depending on assumptions about solar mass loss, tidal efficiency, and the Sun's exact structure during the late giant phase. Observations and calculations indicate that it remains uncertain whether Earth is ultimately engulfed by the Sun's outer layers or survives in a slightly more distant orbit after severe heating. What is not uncertain is that the planet's surface is destroyed as a habitable environment well before this final question is resolved. If Earth is engulfed, the process is not like a solid object falling into a hard fire. The outer layers of a red giant are extended and relatively diffuse compared with the present Sun, though still extremely hostile. Earth would move within a hot gaseous envelope, experiencing intense drag, heating, and loss of orbital energy. Under such conditions, the planet could spiral inward and be destroyed. If Earth is not fully engulfed, it still endures extreme irradiation. Its surface rocks may partially melt on a global scale. Its atmosphere, whatever remains of it, is stripped, heated, and chemically altered beyond recognition. In either case, the old Earth ends. The red giant Sun also changes brightness over time rather than holding one simple value. Stellar models show stages of expansion, contraction, and renewed expansion associated with internal changes in fusion and core structure. One of the most important later events is helium ignition in the core, when helium begins fusing under intense conditions after the contracting core reaches sufficient temperature. For a star like the Sun, this transition occurs after the red giant branch has already transformed the star dramatically. The fine details of luminosity and radius through these stages are matters of stellar modelling, but the broad picture is strong. The Sun becomes vastly brighter than today and reaches a size that profoundly threatens the inner planets. Mercury is expected to be lost. Venus is almost certainly lost. Earth stands near the boundary where outcome becomes less certain in detail. Mars lies farther out and is not destroyed in the same way, though its own future is also transformed by the new solar environment. Earth's location makes it one of the most interesting cases in late solar evolution. The planet may survive as a scorched remnant or may be consumed. Scientific uncertainty here is honest and limited to the exact final orbital result, not to the overwhelming severity of conditions. During the red giant phase, the Sun's light would dominate the sky in a new way if any observer still existed to see it. Its apparent size would be far larger. Its colour would shift toward orange and red tones because of the cooler outer surface. Yet despite the cooler surface temperature, the total heat delivered to Earth would be immense. The paradox is resolved by scale. A cooler but vastly larger star can radiate much more total energy. Earth would receive that energy at levels far beyond the tolerance of oceans, rocks, or atmosphere in their previous forms. The expansion of the Sun therefore marks the final transformation of Earth from a once living planet into a terminal world under direct stellar assault. All earlier changes, though vast, still occur within the life of the Sun as a main sequence star. The red giant horizon is different. It is the stage at which the star itself becomes spatially enormous and physically capable of overwhelming the inner solar system. Earth's fate is then tied not only to climate and atmosphere, but to the changing body of the Sun itself. The planet that once rests in a long habitable interval now faces the swollen outer layers of its aging star. And the last question becomes not how Earth lives, but whether any planetary remnant remains at all. What remains of Earth after the Sun's late evolution depends on a final uncertainty in orbital fate, but not on the broader direction of change. By this stage, the world that once carries oceans, air, and a dense surface biosphere has already passed through long drying, atmospheric loss and extreme heating. The final Earth is therefore not a living planet in any familiar sense. It is a remnant. Whether that remnant survives as a separate body or is ultimately drawn into the outer layers of the giant Sun remains uncertain in detail. Observations of stellar evolution, planetary dynamics, and the physics of tidal interaction define the range of likely outcomes, even if they do not settle every part of the ending. If Earth avoids complete engulfment, it does not remain intact in the old surface sense. The atmosphere is largely gone or transformed beyond recognition. Any remaining gases are thin, unstable, and vulnerable to escape under intense heat and solar radiation. Surface water is absent. Hydrated minerals, meaning minerals that contain water within their structure, may have long since broken down in many of the upper layers, releasing vapor that is then lost. Organic matter no longer shapes the surface. Carbon once moved through forests, soils, plankton, and air. But by this stage, those rapid cycles have ended. The remnant Earth is dominantly mineral. Its surface would likely be heavily reworked by heat. Rocks that once remained solid under ordinary conditions can soften, partially melt, or chemically decompose when subjected to much greater flux from an expanded Sun. The degree of melting depends on the exact luminosity, orbital distance, albedo, and duration of the most intense phases. It remains uncertain whether surviving Earth, if not engulfed, would experience a complete global magma ocean or a more complex pattern of widespread surface melting and recrystallization. What is well supported is that the outer layers would be profoundly altered. The crust would thus preserve ordinary landscapes, mountain ranges, basins, shelves, and dry plains would lose their earlier forms under thermal damage, collapse, and possible resurfacing by molten or semi-molten material. The planet's bulk interior, however, is not erased as quickly as its surface. The mantle still contains the deep thermal structure built across the whole history of Earth. The core still contains its iron-rich interior unless the entire planet is destroyed. If a remnant Earth survives outside the Sun's envelope, it may continue as a rocky body with differentiated layers, meaning the same large-scale separation into crust-like outer material, silicate mantle, and metallic core. Yet the outermost expression of those layers would be transformed. The familiar interface between sky, sea, and land would be gone, replaced by a barren surface shaped primarily by heat, radiation, and the slow cooling that follows the most violent stellar stages. The Sun itself does not remain a red giant forever. After later stages of instability and mass loss, it eventually sheds its outer layers and leaves behind a dense remnant called a white dwarf. A white dwarf is the hot, compact core left after a Sun-like star exhausts its main nuclear-burning phases. It is very small compared with the giant star that precedes it, but it begins extremely hot and then cools slowly over immense spans. If Earth survives long enough as an independent body, it would then orbit not a swollen red giant, but this dimming stellar remnant. By then the main destruction has already happened. The question becomes what kind of object continues around the white dwarf, if any. A surviving Earth in orbit around a white dwarf would be cold on its outermost surface after sufficient time, but not restored. Cold does not mean habitable. By then the planet would lack oceans, an active biosphere, and likely any substantial atmosphere of the old kind. Its surface materials would record earlier heating and stripping. Impacts from surviving debris in the altered solar system might continue to scar it. The orbit itself would be wider than before because of the Sun's mass loss. Assuming the planet survives the giant phases, the new solar system would be quieter in light, dimmer overall, and organized around a stellar ember rather than a stable main sequence star. If Earth does not survive, then no remnant planet remains in the ordinary sense. Its material would be mixed into the giant Sun's envelope, or otherwise broken apart during engulfment and drag. In that case, the memory of Earth would continue only in redistributed matter, not in a coherent world. Some heavy elements from the planet might later become part of the Sun's lost outer layers, or be incorporated into debris around the white dwarf stage. Astronomers observe signs of disrupted rocky bodies around some white dwarfs, where planetary remnants pollute the star's outer layers or form dusty disks. These observations show that planetary destruction in aging systems is real and physically plausible. They do not prove Earth's exact end, but they support the range of outcomes in which a rocky planet can be disrupted or consumed during stellar evolution. The final state of Earth therefore sits between two scientifically grounded pictures. In one, Earth survives as a scorched mineral remnant orbiting a white dwarf, stripped of ocean, atmosphere, and life, with its surface profoundly altered by former red giant heating. In the other, Earth is engulfed and loses its identity as a separate planet. The uncertainty rests mainly on tidal effects and detailed solar mass loss history during the giant phases. Those are difficult to calculate with complete precision far ahead, because they depend on internal stellar structure and orbital response. Yet both paths agree on the deeper point. The habitable Earth ends long before the final orbital verdict. What remains most certain is the order of loss. First the climate balance fails, then surface waters retreat, then the broad biosphere declines and contracts, then the outer planet is stripped to a harsher mineral state. Finally, the changing sun imposes conditions that either reduce Earth to a scorched relic or erase it as a distinct world. This sequence is not driven by accident. It follows from established stellar evolution, atmospheric physics, geochemistry, and planetary dynamics. The remnant Earth, if it exists, would be strange not because it is mysterious, but because it is exact. A world once defined by blue oceans, white clouds, oxygen-rich air, and a living surface would persist only as rock and metal under a deadened sky. Its continents would no longer be continents in the old sense. Its oceans would no longer be basins of water. Its atmosphere would no longer soften light or carry weather across the globe. The planet would remain only as structure, memory written into layers, and the final consequence of a star that ages according to the same rules seen throughout the galaxy. The long future of Earth unfolds without haste. The changes are immense, but they do not arrive as sudden breaks. Light increases, air shifts, water rises into the sky and slowly leaves, continents dry and harden, life withdraws from open land and sea, then survives only in rare sheltered places, and then no longer shapes the planet at all. Beneath these changes, rock continues to move in silence. The mantle carries heat upward. The core maintains its hidden circulation. The magnetic field extends into space for far longer than forests, clouds, or shorelines remain familiar. Earth's future is strange because the planet does not fail in one way only. It changes layer by layer. The outer sky changes first, then the climate, then the waters, then the living surface, then the ground itself. Deep inside, the old geological engine continues almost unchanged while the exterior becomes less and less like the world once known. In the end, even that persistence meets the larger life of the sun. The star that makes Earth possible also sets the limit of Earth's long survival. What remains most peaceful in this view is the order of it. Nothing in the process is arbitrary. The same physical rules that shape distant stars, dry worlds, and ancient rocks also shape the last path of Earth. A planet can remain beautiful and temporary at the same time. It can hold oceans for billions of years and still move, by slow degrees, toward heat, silence, and stone. For a very long time, Earth remains a world in motion, carrying air over land, light over water, and deep heat below both. Then, over longer time still, it becomes a record of what planets do when stars grow older. Its future is not hidden. It is written quietly in sunlight, atmosphere, water, and rock, and it unfolds with the same patience as the cosmos around it,